So you've got your graph and all your results. Now it's time to talk about it, and that's where the discussion or analysis comes into play. This is several paragraphs. Remember, this and the introduction are generally your largest chunks of text. It's several paragraphs that analyze the results and evaluate your investigation. We generally split this into 3 paragraphs. Your first one is just talking about the data. So this is just explaining in words what the graph shows, discussing any relationships, maximum, minimum, etc. So you may say the data in figure 1 or graph 1 shows a maximum value obtained at this with a minimum value obtained at this. The R-squared value represents a linear line with an R-squared value of this. You're really just explaining what the graph does, almost as if we can't see the graph, but you're just summarizing all of the key important factors from that graph. The second paragraph is then justifying or explaining the results. So this is using the graph, so linking back to the graph or your trend line, your line of best fit, whether the hypothesis was supported. So this is really the first time that you're talking about supporting the hypothesis. You identify and discuss any unexpected results. This then will link into random errors in the next section. But you're also justifying your results. So you're linking back to the scientific theory to explain why you got what happened. So you might say, as shown in figure 1, the height of the plants increased at a linear rate as the volume of water increased. This can be explained because plants absorb water to generate nutrients. More water would result in more nutrients to the plant, which would provide more opportunity for growth. Something like that. So you're linking back to the science and going, this is why I got these results. If your results don't make any sense, you can't justify them because they go against everything you'd expect. That's okay, but just explain that. So you would say something like, the expected result was this because of, however, the results in the graph do not support this. This could be why. So this could be due to errors, or this could be because of this. But firstly, you're still linking to science because you're explaining, well, why did you expect a different result? And you're clearly outlining that the result you got is not what you expected. So first paragraph, explaining the results. Second paragraph, really justifying the results and mentioning whether the hypothesis was supported. The third paragraph is now errors. This is talking about your errors. So to start off, to summarize the 2 types of errors we have random error, which we often talk about as scatter. So this is scatter or variation between trials. This means that something changed constantly. So inconsistently throughout the experiment, something was affecting your values by different amounts. This is linked to precision. So random error could be, often random error is things that you do yourself or by hand is never consistent. If you're using a stopwatch, your accuracy of pressing the button, visually observing when to press the button, that's never perfect. So that's always going to be fluctuating. So that's an example of a random error. Systematic, however, is something in the experiment affected all of your data the entire time. So all of your values follow a consistent pattern, but they are too high or too low for maybe what you'd expect. And we'll talk about how you can see that from a trend line. Systematic errors affect the accuracy. So to represent that with a picture, consider it as shooting at a bullseye. The top left, we would say if you hit, you're closely grouped and you're in the bullseye, we would say you are precise and accurate. In this example, you're precise because you've got a very small grouping. So remember, precision and random errors go hand in hand. So your shots are not random. You can hit the same point in a very small group accurately, but you're off from the expected value. You want it to be here, all of your values have shifted to the right. So in this case, if you were, say, using a rifle to shoot, you need to adjust your scope. So you were shooting with a bow and arrow, you need to aim more to the left. So you're off by an amount. In this case, we would say you're accurate, but you're not precise. Remember, accuracy is systematic. So we would say you're pretty much hitting all of the same points. You're very close to the middle, but you're scattered all over the place. So precision is random. So your shots are all over the place. But in general, you're surrounding the target. So you're kind of aiming at the right spot, but your grouping is so blown out that you're just jumping all over the place. And then in the last example, you are neither precise nor accurate. You haven't even sort of hit close to the target, and you're scattered all over the place. So not only do you need to adjust your aim, but you need to work on your randomness of your shots to reduce that grouping. To link that to a graph, here we can see we've got a lot of scatter from very low precision. So remember, precision is random errors. We've got lots of random error here. We can sort of generally see that we're following an increasing pattern, but the values are just bouncing all over the place. So it's very, very random. In this case, we've got much higher precision. So we've got a lot less scatter all over the data. There's a few points that are above and below, but a lot of them are very, very close. So that is much less random error, but still evidence of random error. So on a graph, random error looks like scatter. Looks like values that are jumping around the place. We can also see it in the table. If you do trials, if you see the value is changing between trial 1, 2, and 3, that's an example of random error because they're not getting the exact same value. Systematic errors are harder to identify. Generally, the best way to tell that you have a systematic error is when you construct your trend line. If it doesn't pass through the origin, that 0, 0 point, and you expect it to, it means that all of your values have shifted up or down by some amount. For example, if we look at plant growth versus volume of water, and that's a linear relationship, a straight line, we would expect that at 0, the plant height would be 0. If we give a plant no water, it's not going to grow. But if you plot your line and for no water, it's all the way up here at like 30 centimeters, that probably suggests there's a systematic error. Something has happened in your experiment to all of your values to increase it by 30 because you know it should pass through 0. So that's how we identify systematic error. So within your error discussion, you need to identify the most significant. A lot of people just go, this could have happened, but really if it's a bit of a stretch or it's not a really important error that hasn't contributed significantly, I would leave it out. Stick with the main obvious or most impactful versions. Explain how they would have affected your results. So this is really important. A lot of people just say, this is the random error, but don't link back to what did it do to your data? How do you know it was there? So you're talking about the random error would have produced scatter, and you can say this can be seen in graph 1 where. Same with systematic. This would shift all values. This can be seen in the graph where the trend line does not pass through the origin. Something like that. Worth including a suggestion of how you could minimize. So you've explained what the error was, you've stated whether it was random or systematic, you've linked it to what it did to your data or how you knew it was there from the data. Then you can just have a quick sentence that says, how would you minimize this error in the future? So this error can be minimized by increasing number of trials, by repeating an experiment with a different apparatus, something like that. One thing I would say is that you always talk about minimizing errors. You cannot eliminate errors. It's nearly impossible to eliminate completely a random or a systematic error. They're always there, but we can minimize them. So we use that word instead of we can eliminate this error. Avoid terms like mistakes or risks, because again, a mistake or a risk is very different. If you make a mistake, the expectation is you knew about it, so you should have fixed it or remeasured that value. Errors are different. We don't know an error is there until we've got all of our data. And again, as I said, you can't fix or eliminate an error, you just minimize it. In general, 2 random errors and 1 systematic error is enough for a prac report. If you explain them in good detail, that's a really good amount. You can certainly have more, but remember that quality is better than quantity in a practical report. It's better to be detailed and highlight the 2 most important random and the most obvious systematic than just go, here's a huge list of possible errors. As I said before, random, a really common example is things that you do yourself, like manually operating a stopwatch, observing something with your eyes. Often we talk about that as human error. That's the best way to describe it. It's the error of being a human. We're not perfect. But don't use that term in a practical report. So don't say a random error is human error. It's too vague for what we want. Instead, you can say something like the manual operation of the stopwatch, or the fact, or the manual dropping of the object would cause a random error. That's a much better way to say it than a a random error in this experiment was human error. It's like, it's just too vague. So be specific. Lastly, in terms of systematic, again, I think the problem becomes that often in lower levels you're taught that a systematic error is most of the time caused by calibration errors, as in if you're using a digital balance, a set of scales, and it's not zeroed properly, all of the masses that you weighed out are going to be higher or lower than their real value. So often people just write calibration error in their prac reports. It's not great. Don't use the word calibration error or faulty equipment. Instead, be more explicit. So again, you could say that whilst the masses used were not measured, they were marked on them. So like those little brass weights that we use have like 50 grams stamped in them. You can say that whilst the brass masses were stamped at 50 grams, this may have not been the actual mass. Given that this was used for everything, this would create a systematic error. Rather than just saying the equipment was faulty, or rather than saying that the digital balance may have been miscalibrated, you can say that whilst the digital balance was used, the values may have not been accurate to what was used, something like that. So see the slight difference between faulty and just saying a calibration error to being very specific as to what it was. So let's look at some examples. So this is some past student work of really good examples of error analysis. So here, how you lay it out, it's entirely up to you. This one, they've given us a nice little picture and a heading. So random error 1 was dropping position. You can see that they've stated what it was. Plasticine sometimes falls in a horizontal position, sometimes more vertical. This displayed in the results were the yellow marked in table 7. So in their example, they highlighted their table and made it really easy for us to see there was a couple of dodgy results that were clearly scattered, random error. They've then sort of explained, blah, 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 this is why it happened. Then they've said, so it travels through a narrow gap between the plasticine and the wall cylinder. Sure. So really what we're looking for here is they've said it results in a stronger drag force. Refer to equation 2. So they were calculating the force. They've said the effect it has on the data. Where do you see it? What effect did it have on the data? What was the error? That's a good example. In this one possible random error is the collision of the balls inside the glass jar, which would have decreased the fall time on the plasticine. So here's the error. Here's the effect on the data. They've gone into a bit more detail to say how it was all done. This would decrease the time taken. So again, we're expanding on what it would do. This error would reduce the accuracy and precision. That bit, not so good. Don't like that they've used accuracy and precision because you can't affect both. You can't have random and systematic at the same time. And then lastly, this can be seen in the third trial. So this is where we see it. So we're following a pattern. Error, effect on data, evidence for it. Last one. In this experiment, a bubble repositioned itself, blah, blah, blah. This affects the straight line descent. So they're explaining what the thing was. Source of random error. So again, they've clearly, in this case, they gave it headings. In this case, they've just used it in the paragraph. They've said the particles behave randomly between each test. This affects the overall fall time. So this is the effect on data. However, in this case, they've said, despite that, has a relatively good R² value on the linear line. It's likely that it has reduced the influence throughout the experiment, blah, blah, blah. So they're basically saying it hasn't affected it too much, but this is what it would do to the data. This is what the thing was. So examples of error paragraphs. So this would be one random error for each of these examples. So you'd have 2 of these and 1 for a systematic.